Hey everyone, today is about segment proofs. So this is the first section of our geometric proof section, and I'm going to go through a couple postulates and definitions that you're going to want to use in this section, and then we're just going to jump into two examples, and then we'll do more practice in class. So the first thing I want to talk about is the segment addition postulate. So the segment addition postulate says if you have 3 points that are collinear, and more specifically B is between A and C. Now the letters don't matter as long as one point is between some other two. Then what we can say is that the two smaller segments, so AB and BC, would add up to equal the largest segment. So that's what this equation right here says. AB plus BC is equal to AC, because we don't know if there's a midpoint. All we know is the two smaller ones add up to the larger one. All right, so that's going to be very helpful in geometric proofs. The other properties that you're going to see are reflexive, symmetric, and transitive. You'll see these a lot. So remember, reflexive says something is congruent to itself or equal to itself. Symmetric says we take two things and we flip them. For example, might look like this. Okay, and then the last one, transitive, where we said if A equals B and B equals C, then A has to equal C. So this is not new. We've just talked about those in the algebraic properties, but we're going to use them in geometric proofs as well. Okay, and then definition of a midpoint. If they tell you a point is a midpoint, okay, so for example, they tell you H is the midpoint of this segment, then what that means is we can say segment GH is congruent to segment KH. Right, because we know that the midpoint splits something in half. So notice that's a big difference between this midpoint and the segment addition postulate, because here in the segment addition postulate we don't know that B is in the middle. We just know it's somewhere on the line, so we have to use addition to set up an equation versus making things congruent. Okay, and then the very last and probably the most important one you're going to see is called the definition of congruence. And we're going to be talking about definition of congruent segments, but what that does is if I tell you two segments are congruent, maybe segment JK is congruent to segment LP, what I can do by using this definition is make these two segments equal to each other, and that allows you to be able to manipulate them and use them in different equations by saying, okay, yes, I know they're the same size and shape, but now I know their measures are equal, so I can add their measures to different things. I can make them equal to different things. So you're almost always going to be using this anytime you see congruent. If you're going to be doing equations or anything like that, you're probably going to make it into an equal sign using definition of congruent segments. Okay, so this is really, really important that you know this one and you ask questions if you're not sure. All right, so we're going to start with our first example of a proof. Just like the algebraic proofs, we're going to do two columns. So I have my statements and my reasons. This one doesn't even have a picture with it because it's a lot more simple. So they tell you that given segment AB is congruent to segment CD, and they tell you segment CD is congruent to segment EF, the goal is to prove AB equals EF. Notice we went from congruent to equal, so that means we're going to have to use that definition of congruent segment somewhere. But we just want to write down what we're given with. So remember, we always start a proof with the given. So I'm just going to rewrite that. So AB is congruent to segment CD, and segment CD is congruent to segment EF. So always start with the given, and then we can kind of do a little bit of thinking. Well, how can I get AB and EF together? Well, if you notice, AB and EF are both congruent to CD. And if you look at this, this looks like the transitive property. If AB is congruent to something, and that something is congruent to EF, then I can make these two segments congruent. Okay, so I can say that segment AB is now going to be congruent to segment EF, and the reason is because of the transitive property. Okay. And then the very last step, we're almost there. We have AB and EF, but now we want it to be equal. So to make this change to an equal, where we're talking about the measure, I'm going to rewrite my letters. So AB is equal to EF. And the reason I can change that is because the definition of congruent segments. Okay, if I know the segments are congruent, I can say their measures are equal. And that's it, because that's what we wanted to prove, so that would be the final equation.